Welcome to our lesson on the torque. So torque is another concept from physics, but we're going to see it's related to what we've been doing with the cross product. Okay, so torque's one of those words you've probably heard before, sort of in everyday life, but you might not know necessarily what it means, or at least, from a technical perspective what it means. So torque, let's think of an example. Let's say this is a screw, and you want to unscrew the screw, or screw it in. Actually, it doesn't matter if you're screwing it in or unscrewing it. And this is our wrench. This nice line is our wrench. So we're going to use that wrench to unscrew the screw. Guess I need an N in there. Wrench. So we're going to need to apply a force to the wrench in, let's say, this direction. So that's F, the force. I should draw the arrow that way. So we're applying this force to the wrench. So that force is going to cause the wrench to move this way, and it's going to cause the screw to rotate. Torque is just a measure of how much this force is causing this screw to rotate. So torque is a measure of how much force causes an object or a point, something, to rotate. So that's a very loose definition. You might get a more technical one from a physicist or a scientist, but it's a good intuitive definition, and it explains what's going on. Okay, so torque, we're now going to relate it to the cross product. Torque, we're going to use the letter, this looks like a T, it's the Greek letter tau, so this is the letter we use for torque. Okay, so torque is going to be equal to, well, before I give you what it's equal to, let's just kind of explain why it's equal to what it is. Okay, so think about torque is a measure of how much this thing is going to rotate. Well, you can sort of think about what's going to cause this to rotate. Well, the force, right? So the bigger the force, or the bigger the magnitude of the force, the greater the tendency for this to rotate. So obviously the force is going to have an effect on it. But the other thing that's going to have an effect is this length right here. You can imagine if this was a wrench and you applied the force at the end of the wrench, that's going to be a lot better than, say, applying the force, right down near the handle. It's going to move a lot better if you apply the force down here as opposed to up here. So the greater the length of the distance from the point of rotation to where the force is applied, the more the object will rotate. So that's another factor, the magnitude of this distance, which you can think of as, so distance from point of rotation to the force. So these two things are going to affect how much this object rotates. So that's basically it. There's one more thing. Well, actually, no, I can write down right now. So it's basically F and R. So the way we define torque is F cross, oops, sorry, I did that backwards. It's R cross F. Okay, so it's a cross product of R and F. So one thing to notice here is a cross product's a vector. So torque is a vector. And if you remember cross product, it's a vector which is both perpendicular to both R and F. And it's tough to give a total good explanation of why that is, but one way I like to think of it, and this is not exact, but with this wrench example, think about, the right hand rule. If R was your index finger and F was your middle finger, then your thumb would be pointing sort of straight up, straighter to the screen. Well, which way would the screw be going? If you were unscrewing it, it would be coming up, right out of the screen. So that's kind of like why I think of it, although that's not exactly what's happening, because there's other things you can rotate, like a bike pedal where, the axle isn't coming out. So it's not really, the same, but, I like to think about it that way. It just kind of helps explain to me why the torque should be perpendicular to both the force and the axis of and the arm here. Okay. So another thing that's useful with torque is the magnitude of torque. So the magnitude of torque will be equal to the magnitude of R cross, the magnitude of R cross F. And why should that be? Why should it be equal to the magnitude of R cross F? Well, we know the magnitude of the cross product is equal to the magnitude of R, the magnitude of F times sine of theta. So I'm going to draw another picture of R and F here. So R is this vector going from the point of rotation to the point where the force is applied. Here's F. Let's say F isn't applied perpendicularly. Let's say it's applied in this direction. So theta would be right here. Okay? So remember, F is now made up of two components, right? This component and this component. We'll think of this component. We'll call this component is perpendicular to R. So we'll call that F perpendicular. And then this component is parallel to R. Well, which parts of these forces is actually going to be moving the wrench or whatever this is? Only this thing, right? If the component that's acting parallel is not doing anything to rotate the object, so it's really just this component here that's doing all the turning. And what is this equal to? Well, it's the opposite side to theta, so it's equal to, this is equal to the magnitude of F sine theta. Boom, right there. So, that's where this comes from. That's what you need to know. So let's just do one example to see how to do this. So here's an example. A mechanic exerts a 20 let's just say it's 20 Newton force. I don't want to worry about the converting. A 20 Newton force at the end of a 10-inch wrench. 10-inch, let's say 10 centimeter wrench. If this pull makes an angle, I don't know what that means. Well, the force he pulls. Okay, so the pull makes an angle of 60 degrees with the handle. What's the torque produced on the nut? Okay, so here's the nut. N for nut. Here's the wrench. Is it a wrench? Yeah. So it's 10 centimeters. I'm going to write this in meters. So that's 0.1 meters. And the vector is in this direction here. And then it makes an angle of 60 degrees with the handle. So if the vectors make an angle of 60 degrees, so here's our force. This must be 60 degrees, right? So the angle between this vector and this vector is 60 degrees. So that means the torque. What is the torque? So there's two parts, right? What's the magnitude? So that would be the magnitude of F, magnitude of R. Usually I wrote them backwards, but it doesn't matter, right? We're just multiplying. Times sine theta. So the force is The force has to be in newtons. So 20 newtons times 0.1 meters times the sine of 60. So that's 20 times, so it's 2 times the sine of 6, which is root 3 over 2. Oh, I forgot the units, but I'll write it at the end. So 2's away. So it's just root 3, then Newton meters. Okay, so that's the magnitude of the torque. Comment about the units. So this is the units on torque, Newton meters. You might recognize that from work. Remember, we call these joules. Newton's meters, when we're talking about work, was called joules. When you're doing torque, do not call them joules. So, not referred to, not called. So when we do, because torque and work are totally different concepts. So even though like dimensionally they're the same, Newton meters, they don't mean the same thing. So not called joules. And you will, like I think our textbook does, and it really shouldn't. Okay, so it's Newton meters when you're talking about torque. So that's the magnitude of the torque, but I still haven't said what the direction, right? Torque is a direction, is a vector, so it has a direction too. So you just have to think about right hand rule, right? This would be your index finger. This would be your middle finger. So if that was the case, then your thumb would be pointed down. So the direction, based on the way I drew it, is into the page or into the screen. If I had drawn it, this way, then it would be up, but that's the way I drew it. Okay, so that's a simple, quick example for torque.